Everyone can hear me okay? Good? Okay. All right. So I'm going to talk about a filter function approach to for adiabatic quantum control, and in particular how it can be used for adiabatic quantum computing as well as quantum annealing. So exactly what does that mean? So let me see. No, that's not going to work. So really what I want to develop is a theoretical framework for examining the effects of variations in the quantum annealing schedule, as well as the effects of the environment on the system in the frequency domain. And so in particular, I want to focus on noise processes that are temporally correlated, and so I know typically not non-Markovian. And so this is typically useful in cases of optimized control, as well as where one perhaps wants to generate a annealing schedule that enhances the probability of being in the ground state while simultaneously mitigating the noise. Also in the case of noise characterization, where one may want to use the adiabatic quantum system to sort of probe the surrounding environment and learn something about the actual noise processes that sort of plague its dynamics. So the reason why is that actually this filter function formalism has actually been quite a useful tool in optimized control and noise characterization outside of the adiabatic community. In particular, the filter function formalism, what it does, and I'll discuss obviously a lot more about that later, it gives us a way of sort of describing the control of a quantum system in the frequency domain. And so in the optimized control case, there's been a lot of theory to develop this, as well as some experimentation, which has been very nice. And also in the characterization side of doing what's known as quantum noise spectroscopy, as I mentioned, using a quantum system to probe its environment. And there's been a number of theory papers focused on considering noise processes that are non-Gaussian, as well as those that are, kind of the nice stationary Gaussian processes, and also considering things going from not only single qubit, but also multi-qubit systems. And there's been a number of experiments, actually, even recently, that there's been quite a number of interesting experiments doing this on superconducting qubit systems. But the one issue is that these methods, the filter function does not really necessarily, it's not really amenable to considering sort of large-scale systems. And this can be seen just from looking at how one does characterization, for example, for a multi-qubit system. Doing even 2-qubit noise spectroscopy can be quite difficult, characterizing all of the noise spectral densities that plague each individual qubit, as well as the cross correlations as well. And so if we were to try to scale this method up, we want something that we can implement on a device, on a quantum computer, whether it be adiabatic or gate model based, that is scalable, that allows us to do this, to characterize the noise on the device during a calibration phase prior to actually running an algorithm. So I think there are many different ways of sort of approaching this problem. I think from the adiabatic case, it makes a lot of sense because we can say we don't necessarily care about the entire spectrum of an adiabatic Hamiltonian. What we really care mostly about the transitions out of the ground state. So basically the low energy manifold is really kind of where we can sort of focus our attention. And in this case, we may actually be able to scale these methods up a bit more. So I'm going to discuss a little bit about the formalism itself and show you some examples of these filter functions in the adiabatic regime. And just sort of tell you some of our ideas, at least for noise spectroscopy, doing actual characterization using this technique, obviously very briefly. So when we talk about an open quantum system, we typically partition in a way where we have a system Hamiltonian, which governs just the pure system dynamics. And this can be, for example, in one case, doing dynamical decoupling, strong, fast pulses on the system, or sort of in the opposite regime, sort of very slow dynamics corresponding to something like an adiabatic algorithm. We have terms that we can characterize as being purely corresponding to the bath, and as well as a term that we typically correspond to the system environment interactions. And these bath operators can be quite general, right? I mean, they can correspond to time-dependent operators that are maybe they're quantum. They correspond to quantum noise. They correspond to classical noise, right? But there are correlation functions that one can relate to these operators. So when we actually go to measure an observable, what we typically do is we evolve the density matrix and we measure the observable, right? So in this case, what I'm going to do is I'm going to say, okay, let's assume that the pure bath term is essentially not there, so it's identity. And let's move into the rotating frame with respect to our system term. And so we can write essentially the rotated dynamics or the full dynamics in this way. where we have an error term as well as a term which is the pure system evolution. And so if we make an additional assumption here, just for sort of simplicity reasons, that the control implements something like a no-op gate, so basically dynamical decoupling, we want to implement at some particular time, we want to implement an identity operation, then this expression gets a lot easier. And what we can do is we can actually use the cyclicity of the trace to kind of move everything around here to kind of focus all of the error terms sort of right here. And notice here that I have these ensemble averages here as well, just in case, because of course I said generally that this is these can be quantum operators, these can be classical operators, right? And in particular, it can be both, right? We can have both present. So what's nice about this is that we can sort of capture all of the averaging, essentially all of the aerodynamics, the average aerodynamics here by this term. And what's nice about this is that we can actually expand this out into what's known as a cumulant expansion. And so essentially all of the terms of the perturbation expansion are captured within these cumulants here. And so this is sort of, you can think of this as sort of a Magnus expansion, essentially, but for operators which have some statistical properties. They have some correlation functions associated with them. So let's look at a particular case. So if we think about sort of the case where we have just dephasing, and our noise is Gaussian and stationary, we find that actually the entire expansion truncates up to second order. So we only care about the first cumulant and the second cumulant. If we make the assumption that the noise is zero mean as well, then we actually the first cumulant goes away, because this is essentially just an average over the Bath operator terms. So what we really have in the end is this second order cumulant here, where this term right here, I should say actually, so I'm assuming here the control is bang bang, so hard and strong pulses. And so in this case, these all of the effects of the control can be basically captured by what are known as these switching functions. And this is sort of just this is a non-adiabatic case, right? This is just sort of the general theory. And so we have these terms which represent the switching functions as well as this 2-point correlators. And if we move into the frequency regime, basically the Fourier transform of these switching functions corresponds to what's known as a filter function. And so we find basically that the decay of the dynamics is completely captured by this second order term, and essentially this convolution between the frequency response of the quantum system, or in this case of the qubit, to the control, as well as the noise spectral density associated with my environment. And so this can be used in a couple different ways. So if one wants to, for example, perform optimized control, then the idea would be to try to minimize the overlap here, as you can see in the integral, between the spectral density and the filter function. So essentially moving this filter over to regimes where the spectral density is minimal. Alternatively, if one does not know the spectral density, one can use the filter function to essentially probe different frequency bands here, right? So we can move this around, and we can look at sort of the decay rates corresponding to this to the second order cumulant, or to the second cumulant, I should say, based off of sort of where we are in frequency. So we can sort of move that filter around by adjusting the controls themselves. And so what we want to do is we want to extend this idea and see if we can to the adiabatic regime, and see if we can sort of use a lot of this formulation to understand how optimized control as well as noise characterization can be done in the adiabatic setting. So now, instead of having a system term which corresponds to dynamical decoupling sequences, let's look at this as an adiabatic Hamiltonian. And so in that case now, what we're going to do is we're going to do exactly what we did before. We're going to move into a rotating frame. However, I'm going to define the rotating frame a little bit differently than normal, just because, as you'll see later, it kind of helps out with the math. But basically, this adiabatic term here represents our quasi-adiabatic evolution, which of course we always have our pure adiabatic term plus corrections, and then this error term here captures sort of the rotated frame system bath interaction. So nothing here is sort of different than what we've done before thus far, except for sort of the way I've defined this operator. So if we look now at any sort of expectation value of an observable, here I'm color coding the adiabatic Hamiltonian as well as the error Hamiltonian. We see that everything up here looks about the same, And then what we can do is we can actually use cyclicity of the trace to kind of move things around. And so what ends up happening is we get sort of a term here that represents basically kind of like what we had before. These are the faulty dynamics due to the system-bath interaction. And then we have another term here which represents sort of represents the quasi-adiabatic evolution, sort of the pure dynamics without noise. And so, you can see that basically if these were identity, this would essentially be the same thing as the dynamical decoupling case. But essentially this is a more generalized version of that. But we're looking at it here in particular for the adiabatic evolution. So if we assume Gaussian stationary noise, we can truncate the expansion up to second order. We don't get exact cancellation as we did with the dynamical decoupling case, but we can still truncate this expansion, and then this is essentially what the second order cumulant looks like. So if we consider, as I mentioned, the noise to be Gaussian and stationary, then we get essentially 4 primary integrals that all kind of look similar. In the sense that they're all proportional to terms like this. So the I and J over here represents projectors onto the eigenstates of the adiabatic, the pure adiabatic Hamiltonian or eigenstates, and then the alpha and beta correspond to just basically different products of these bath operators. And so in terms of the spectral densities here, these are spectral densities where if alpha and beta are the same, correspond to self-spectral densities, and ones where they're different, these are cross-spectral densities between the noise operators. But the important thing is here we have essentially something that looks a lot like a filter function formalism again. The difference is now that we have it for sort of individual transitions. And I should mention here that this is in the adiabatic limit, so this doesn't assume corrections to the adiabatic approximation. So I'm sort of keeping it simple here, but of course you can imagine that there are additional terms that will contribute here as well. But the point is that we have the same sort of structure here. And the really interesting thing about it is if we look at the filter function itself, we again obtain something that looks a lot like it's essentially a Fourier transform of these switching functions. But these switching functions now are a function of the eigenbasis as well. Basically what that means is that if we change the control, or if we change the specifications of, let's say, the problem Hamiltonian, we actually change the frequency response of the system. We change the frequency response of the system. So basically that gives us it's sort of a different additional, I should say, aspect that we didn't see before in the dynamical decoupling or the non-adiabatic case. So if we look at a sort of a single qubit example here, we assume Gaussian dephasing again. Then we obtain basically 4 terms here. One that corresponds to the basically no transitions out of the ground state or the excited state, and those which are transitions. If we look at so this is here, maybe it might be hard to see. This is the F00 and the F11. For 2 different types of control schedules, one for linear and one for the Roland surf path, which it was originally developed for Grover's algorithm. This is essentially a one qubit Grover problem. We see that the filter functions actually don't look very interesting here. Not surprising, it's a single qubit problem, and we're not really these 2 paths actually aren't too different when it comes to the single qubit problem. But what's interesting about them is kind of something that we already kind of expected to see, which is that most of the frequency response is in the low frequency regime, which is what we expect. When we think about adiabatic dynamics, we think about these paths evolving very slowly. So everything is predominantly focused in the low frequency regime. We see that here, so that makes sense. If we compare this simulation, again, and this is in the adiabatic limit without corrections, if we look at compared to a full dynamic simulation for different types of these are 2 different types of noise correlation times, we see that it doesn't track quite well in the when the noise correlations are essentially the correlation time is short, but when the correlation time is long, we see much better tracking. I mean, of course, this is without corrections, right? So once we add in corrections, we expect to see better tracking, and that's something that we're currently doing now. The more interesting case is when we look at Grover's algorithm here. For Grover's algorithm, basically what we're doing here is we're keeping the linear schedule, and we're just changing the number of qubits. And so what we see is as we change the number of qubits, the filters actually start to shift to higher frequencies, higher concentration and higher frequencies. This is essentially due to the fact that if we look at the energy landscape, the energy manifold, we basically see that the curvature of the eigenstates actually becomes greater for higher values of n. So we see that basically due to the changes in the energy manifold, we see that the filter function is affected, exactly like what we mentioned before. So what this means is that basically we can actually adjust the frequency response of the system by just changing the specifications of the problem. Now, if we look at sort of the less interesting case is sort of if we change the controls themselves, we do see effects of that. Now, you'll notice here though that the roll-in and serve path before actually is the path itself is requires higher bandwidth. So we would expect that it has higher frequency contributions. But actually we don't really see, we see actually the linear path actually has a little bit of a higher frequency contribution than the roll and serve path, and that is due to the fact that the curvature in the energy manifold actually is less for the roll and serve the roll and serve path than it is for the linear case. So here we kind of see the interplay between both of those together. But the important thing is that we see here is that really that the filter function is altered by the control profile as well as the problem specification. So while I think the idea of optimized control is, in this way is actually interesting, I think that the more intriguing thing for me is sort of the potential flexibility that we may have for doing noise spectroscopy. So typically when we think about noise spectroscopy with dynamical decoupling, what we do is we basically devise a sequence and vary the timings between the pulses, and as we vary the timings, we're basically able to move these filters across in frequency. We measure some observable. We measure some observable as a function of time, and then we use that filter function as well as the observables to back out essentially the spectral density, so reconstruct the spectral density. Here in the adiabatic case, the interesting part is we don't only have control over the annealing profiles, but we also have control over the problem specifications. So one of the main questions actually I have is sort of, now that we have these two available knobs, can we sort of think about building adiabatic algorithms that are not necessarily meant to do computation, but meant to sort of probe the environment and learn something about the noise characteristics instead. So I think this is sort of an interesting aspect that we're definitely looking to further explore. So in conclusion, we've extended the filter function formalism to the adiabatic regime. We really want to develop a stronger understanding of these control variations. So how do we do optimized control in this setting? And of course, that there's many more terms to account for. Do we really need to consider higher cumulants than just the second cumulant that we currently have, or we're currently approximating the evolution by? And then looking at applications of optimized control and noise spectroscopy. So with that, thank you for your attention.
Okay, do we have any questions? Okay, I'll start out with a question then.
Yep.
Can you remind me how you actually extract the filter function experimentally?
So it's based off of the annealing schedule, right? So what you would need to know is you need to know the eigenbasis of the adiabatic Hamiltonian, and then essentially which is basically dependent on the control. And so you would need to know that plus the interaction Hamiltonian. And so you basically work out the perturbation expansion. And when you do the time-dependent perturbation theory, the filter function naturally appears.
Okay.